everyone. I'm your host, Amir Jafari, and this is the fourth lecture in the series of lectures on quantum field theory. Previously, in the introductory part for this course, we talked about difficulties in combining special relativity with quantum mechanics, and we learned that generalizing the Schrodinger's equation to the relativistic regime by writing down, relativistic differential equations for wave functions doesn't work because, because of the equivalence between mass and energy in special relativity, writing down a differential equation for a fixed number of particles described by the solution, which is a wave function, is impossible. You have in a relativistic system, you have high energy or fast moving particles, and the this kinetic energy, this high energy, means that it can be converted into mass at some point. So you're going to have new particles popping out. So you need a formalism which allows you to create and annihilate particles. So wave functions are not the center of attention, in a relativistic theory, because they describe a fixed number of particles. Instead, we need this concept of a field, a quantum field, acting on quantum states which can create and annihilate particles. We discussed these. So, where we left the discussion was the Klein-Gordon equation and the Dirac equation. The same arguments that I'm going to have here can be applied to the Dirac field as well, but it's more complicated mathematically because of the spin of the particles. You can have particles which are described by the Dirac equation, like electron and positron. So we're going to focus on the Klein-Gordon equation, this equation here. And as an example, let's see what's going on here. This is the Klein-Gordon equation, okay? And this is the vector potential. And we use this as an example to say that the Klein-Gordon equation as a mathematical equation is not incorrect. It turns out that our interpretation of its solution as a wave function doesn't work. It gives us negative probabilities, etc. Similarly, in the case of the Dirac equation, if we interpret the solution of the Dirac equation as a wave function, we're going to get difficulties like negative energies, etc. So one solution is that instead of interpreting the solution of the Klein-Gordon equation as a wave function, we should treat it as a field. And we briefly discussed the similarity between the Klein-Gordon equation and the equation for the vector potential from classical electromagnetism. If you look at this equation, which can be obtained by writing down Maxwell's equations in vacuum, where there is no electric current, there is no electric charge, then you get this equation, which is basically a field equation. The vector potential, which defines magnetic field by this relation, this is because divergence of the magnetic field vanishes because there is no monopole in the universe. So magnetic field can be written as a curl of a vector potential, of a vector field. And then you can also write the electric field in terms of this field minus some gradient of a scalar potential. So you see the similarity between these equations, and no one interprets this A vector potential as a wave function. So similarly here in the Klein-Gordon case, we shouldn't interpret phi, the solution, as a wave function. We should interpret it as a field. At this point, this is just a guess. We are not proving anything mathematically. This is just guesswork, okay? But it works. So this is the idea, and if you insist that no, the right-hand side of this equation vanishes, you can write it perhaps in this way. This is, I don't have any space over there, so this happens all the time. So I should probably, okay, you can write this way. By the way, here C and H bar unity, natural units. Okay, but mass of photon is 0, so the right-hand side of this equation vanishes. But here we are talking about massive particles, massive and spinless particles. So this is the mass of the particle we are hoping to create, to be able to create and annihilate. Okay, this is what we want. And vector potential, by the way, I'm just using the similarity to make this story very familiar to you, because you have already exposed to classical electromagnetism. The vector potential is a vector. It's a vector field. At any point in space, it gives you a vector. But phi in the Klein-Gordon equation is a scalar. This means that in the electromagnetic case, the particle which you are going to create using this field A is a particle with spin 1 unity, which is the photon. It's the polarization of photon. We're going to talk about this later in details, why we have a vector which has 3 components in space, but photon has 2 polarizations, up or down. But the point is that because photon has spin 1, so here you need a vector field. And here in the Klein-Gordon equation, because we didn't consider spin, so there is no spin here, spinless particle, but it has mass, so we have a scalar field, and mass of that particle appears here. Okay. At this point, we don't know these, but I'm telling you this because we have had some discussion about the similarity in the past, so this story should make sense to you. Okay. So this is what happens in reality when we develop quantum field theory. So the point is that we look at the Klein-Gordon equation as a field equation, not as an equation for the wave function. Now the point, or the next step, is to, let me get rid of these. The point is use the similarity again to quantize the field. What it means that if you think about the radiation field, by radiation field we mean electromagnetic field. Okay. In this case, look, this is a classical field. Classical means that it gives you a quantity, a scalar number at any point in space and time. And this is a classical field as well, because at any given point in space and time, it gives you a vector, right? Classical field. It's not an operator. They are not operators at this point. So, in order to get from this continuous, electromagnetic field picture, Maxwell's equations, electric and magnetic fields, you quantize this field, A, and you get the picture in terms of photons, bunch of particles, which can be created and annihilated. How? Defining operators like these. So you're going to make this A vector potential a quantum operator, so you're promoting a field to an operator, which would create a photon by acting on the vacuum state, the state where you have no particles. Okay, so this way they can operate on quantum states and they can create or annihilate particles. So this is the procedure we are going to apply here. And in this case, for the Klein-Gordon equation, we seek something similar. We are going to quantize the field, which means promoting this classical field to an operator, which means that it's a classical field and at the same time an operator, so it's a quantum field, and this can operate on the vacuum state and give you a particle at that point. It creates a particle. This is the procedure we want to take. This is the second quantization we are going to talk in this lecture. We've briefly discussed this in the past, but we are going to complete it and finish our discussion of quantizing the Klein-Gordon equation in some more details. What's the second quantization? How we quantize these fields, how we promote the solution of the Klein-Gordon equation or the solution of this field equation in electromagnetism to operators, to quantum operators. Well, remember that in the first quantization in ordinary non-relativistic quantum mechanics, we promoted x and p, position and momentum, to position operator and momentum operator. For example, in x representation or space representation, p, the momentum operator, took a form like this, a differential operator. These operators, differential operators, act on, for example, operate on wave functions. In general, they operate on vectors in the Hilbert space, but in wave mechanics, these are just differential equations operating on the wave function. And wave function gives you the probability amplitude, okay? Very simple picture, right? Now, in the second quantization, you say that no, this is wrong in some sense. Why is it wrong? Because it's not compatible with special relativity. Why the first quantization is not compatible with the special relativity? Well, here you say that x space is promoted to an operator, right? And then you have this commutation relationship between x operator and p operator, momentum operator. But in a special relativity, everyone knows that space and time should be treated on the same footing. You are not doing this symmetrical, procedure here. You're not treating space and time on the same footing because you are promoting space to an operator, but you don't touch time. This is against the spirit of special relativity, as we discussed already. So, if you are going to play with the special relativity, then you have to drop this. This is not a very nice thing to do. And if you drop promoting space to an operator, you shouldn't promote momentum either because of this relationship, because we want to keep this commutation relationship. This is the relationship between position operator and momentum operator. If position is not an operator, so P shouldn't be an operator as well. So we say forget about the first quantization. Don't do this. This is not compatible with special relativity. Keep x, space, and time, and p, momentum, as labels. So in first quantization, we kind of, move against the, the picture we've already learned in classical mechanics too. I mean, there, for Newton, for example, position and momentum or velocity of the particle were something very tangible. You have a large scale feeling of these quantities. And promoting these two operators, although it's compatible with the idea that in quantum mechanics observables are represented by Hermitian operators, so x and p are kind of observables, but we want to get back in some sense to Newtonian mechanics, saying that x and p, position of the particle, momentum of the particle, shouldn't be touched. These are just labels. These are just quantities. They are not operators. Instead, what is an operator in the second quantization? The field. The field that satisfies the Klein-Gordon equation, this equation over here. Okay. And also, when we work with electrodynamics, electromagnetism, we say that the vector potential A should be promoted to an operator, but x, t, and p are just labels. Okay, so if instead of x we take phi, instead of p, momentum, we should take some pi, some momentum corresponding to the field. In order to remember what's going on in second quantization, it is useful to think of this similarity here. Look, in the first quantization, you work with x, position, and p, momentum of the particle, okay? And you promote these to operators with some commutation relation between these. In the second quantization, you say that this is against special relativity, so forget about this. Keep x and p as quantities, as labels. Instead of x, work with phi, the field. Instead of position, work with field, phi. And instead of momentum of the particle, use the momentum of the field. We're going to define the momentum of the field in a moment, okay? And instead of this commutation relationship, apply or define a commutation relation between phi and pi. So this is similar to x and p, okay? But because we are working with fields now, defined in the space and time, you have these arguments, x and y, where you are talking about, this field, the value of field at a given point, because it's a field, obviously. So here we have this Dirac's delta. Remember, in 3 dimensions, this would become, let me write this in a more general 3-dimensional space. xi pj is ih delta ij, Kronecker delta, okay? So in 3 dimensions, if you are talking about 3 components of position and 3 components of momentum, the general commutation relation between position and the momentum operator would be something like this. So you are using a similar relation here. Instead of x, you have phi. Instead of p, you have pi, the momentum of the field. And instead of indices, ij, components of the position and momentum, you have arguments in terms of space. And so you have to use the Dirac's equation. So you are basically moving from Kronecker delta to Dirac's delta, from discrete case of components of a vector to a continuous case, because you are in space-time. So, and then we talked about this example of a swimming pool, how we create a particle. We basically spend energy at some point in space, say x, and because of some oscillation there now, you have some waves, and these waves are your particles. So this is the similarity in terms of, just physical intuition between this picture that we are talking about in second quantization, talking about fields, etc., with simple harmonic oscillator. So you can put it this way. Instead of surface of water or depth of water that we talked last time, you take this field, classical field that you have, phi, and if you excite it at some point, x, now x is a label, it's not an operator. This is the reason why we say that don't promote x to an operator. X is just a position, a label in space. It gives you a point in space. It's the coordinate of that point. If you excite the field by spending energy, you're going to get a simple harmonic oscillator there. There is a simple harmonic oscillator there. By spending energy, you are just exciting that simple harmonic oscillator, and its energy is given by a relationship which is familiar from quantum mechanics. And as you spend more energy, you're basically moving from n0 to 1 to 2. You're creating more particles. We discussed this. Okay, so now we need the similarity between simple harmonic oscillator and Klein-Gordon equation in order to write equations and describe this example, this similarity between a swimming pool and a real, quantum field, to see how it works. Okay, how we excite the field, how we get different particles and different energy states, etc. So, if you get back to simple harmonic oscillator in quantum mechanics, let's start with classical mechanics. We started classical mechanics, do the first quantization, and then we move to quantum simple harmonic oscillator. Here we're going to start with Klein-Gordon equation as a classical field, and then do the second quantization and move to quantum field theory. This is the similarity that we have here. Okay, in simple harmonic oscillator, look at the left-hand side. For simple harmonic oscillator in Newtonian mechanics or classical mechanics, in Hamiltonian mechanics, I should say, we have this Hamiltonian. Kinetic energy, this is the kinetic part, plus potential energy of the spring. And this gives you, using Hamilton's equations of motion, or you can use Newton's second law, F equals ma, you get this famous equation, the equation of motion for the mass attached to the spring with angular momentum, angular frequency, sorry, omega. And if you solve this equation, the general solution as a complex solution, basically, you're going to get the real part of this for, you know, to get the real physical position variable. You can write this solution as in this form. A and A star are just constants, complex constants, and E I omega t is just sine and cosine functions, basically. We are using a kind of fancy notation here to say that we know about complex numbers, etc. But in reality, this is just sine and cosine here. We discussed this in the last lecture, okay? Here, we are not showing off that we are aware of complex numbers, etc. No, because of similarity of this form of the solution with the field solution, we are using this form, okay? And from this, when you solve this equation, you get this solution, then it's easy to get the velocity of the particle. Remember, in classical mechanics, the state of a particle or a system is given by its position and its momentum or velocity. So we are talking about position and momentum. Momentum is basically mv, mass times velocity. Velocity is x dot, derivative of position with respect to time. So you easily get the momentum as well, if you like, for the simple harmonic oscillator. Then you say that, well, this is classical mechanics. What about quantum mechanics? Well, you can use this Hamiltonian in your Schrodinger's equation and get the energy, eigenstates, eigenvalues, and wave function, etc. But you can use a Dirac's approach. We did this last lecture. You can say that, well, in the first quantization, as we discussed many times now, you promote x and p to operators and you apply this commutation relation. Then you say that, well, this solution from here, it's easy to see that it is promoted to this. It becomes this relation, basically. Or you can write the position operator in this form for similarity with the classical solution, and momentum as well. This is the Dirac's method. If you remember, we defined this A and A dagger operators, creation and annihilation operators. And then we got the solution. We, from XP commutation relation, we got this relationship between A and A dagger. Now these are all operators. And the Hamiltonian becomes this operator. And instead of X and P, you put these operators and A dagger. You get this Hamiltonian. And from there, the energy is given by this relationship, which is familiar. This is the energy eigenvalue for a simple harmonic oscillator in quantum mechanics. N equals 0 means ground state, n equals 1 first excited states, etc. But we said that, well, you can interpret this relation for energy this way, saying that we have different excited levels of simple harmonic oscillator. But you can also say that, well, when n equals 0, I have 0 particles in simple harmonic oscillator. When n equals 1, I have 1 particle. N equals 2, I have 2 particles. So different vibrations and oscillations in classical simple harmonic oscillator in quantum mechanics can be interpreted as having different particles. So this way you increase the energy of simple harmonic oscillator and create new particles. Okay. So similarly here, now in the second quantization, special relativity plus quantum mechanics, you say, no, this is not the right thing to do. Okay. In general, for the solution of the Klein-Gordon equation, to get the relativistic quantum theory. Instead of x and p to be promoted to operators against the special relativity, we do the second quantization. Instead of x, we have phi, the field, which is a function of space and time. We promote phi to an operator, and instead of p, momentum of the particle, we have the momentum of the field, which we're going to discuss in a moment. And instead of this commutation relation here between position and momentum, now you define a commutation relation between phi and pi. We discussed this already, but we are getting closer to the full description. And then because x, and here there are some coefficients. Last time I guess I wrote them in terms of mass of the particle, angular frequency, etc. I don't write them because the important thing here is just the similarity between these expressions for simple harmonic oscillator in quantum mechanics and the corresponding relations for the quantum field. Instead of x, we have phi, and we know how to define phi. This similarity gave us this equation, which is basically this expression. We got this basically as a Fourier transform. We tried to solve the Klein-Gordon equation by writing down a Fourier transform for the field, and this is just a Fourier transform for the solution. It doesn't give you any physical idea of what's going on. This is just a mathematical expression. But the important thing is the similarity between this expression and this expression for the position operator in quantum mechanics. So you say that, well, here I have these operators now, okay, and then instead of the momentum, simple harmonic oscillator, we have some momentum corresponding to this field. For now, we have no idea what this is. And for Hamiltonian, again, we don't know what kind of Hamiltonian we should define for a field. This is kind of something new. What's the Hamiltonian for a given differential equation? The only thing we have here on the right-hand side is the Klein-Gordon equation. We know that we have this differential equation, the Klein-Gordon equation, okay? And because the Fourier transform of phi gives us this relationship, we use some similarity with simple harmonic oscillator, and we get this expression, but we have no idea about the Hamiltonian or this pi. In this lecture, we are going to finish this basically approach by finding the Hamiltonian and momentum, and then we'll see that we get a very coherent and very consistent picture, okay? And if you know the Hamiltonian, you get the energy. Right, now, how we do this? Well, what we need mathematically is we write this differential equation, the Klein-Gordon equation, and we want to get a Hamiltonian, okay, which, as in Hamiltonian mechanics, in classical mechanics, the Hamilton's equations give rise to the equation of motion. Remember, for example, x double dot minus omega over x for a simple harmonic oscillator corresponds to this Hamiltonian. And I wrote this before, okay? So if you write down the Hamilton's equations of motion, and I'm assuming that you are familiar with the main ideas in Hamiltonian mechanics, otherwise we should talk about this perhaps in another lecture. There you get, these are Hamilton's equations in this case, which is simple enough to, so here you're going to have DHP, P, what you get, minus P dot X dot. These are Hamilton's equations. And you get dH over dx in this case would be m omega square x, which is basically kx, and this is equal p dot is basically dp over dt force minus kx. You get the equation of motion for the simple harmonic oscillator. Hooke's law equals ma, f equals ma. And this is basically the definition of the velocity, right? You can, from here you get this, because, and this is p over f, the velocity. But we're not going to do this in this form. It is easier or more common, or I don't know, I like it that way. It's easier to find the Lagrangian, okay, and after you know the Lagrangian, Hamiltonian is just the Lagrange transform of the Lagrangian. So the idea is that whenever you have a differential equation in physics, this is going to happen very often actually in our study of quantum field theory. You have a differential equation like this, the Klein-Gordon equation, okay? You want to find the Lagrangian. Then, if you do Lagrangian, it would give you, which is a function of these variables here. And after finding that, you can find the Hamiltonian, because Hamiltonian is the Lagrange transform of the Lagrangian, okay? So, what we do, let me very briefly tell you or remind you of how we do this in classical mechanics, and then get back to this problem very quickly. Suppose that you have a Lagrangian, which is a function of x and x dot, okay? Position of the particle and velocity of the particle. Then momentum, the conjugate momentum, is defined as dl over dx dot, okay? And Hamiltonian, the Lagrange transform of this, would be px dot minus L. Basically, what you do is that you say Lagrangian is a function of position and its derivative, or velocity, and Hamiltonian is a function of x, coordinates in general. You're going to deal with generalized coordinates, but we are talking about a simple case. You can call it just x variable, position, and momentum. So this transformation between these two functions is called Lagrange transform. Instead of velocity, you use momentum generally. So, for example, for the simple harmonic oscillator, L is mv square, v is x dot, minus 1/2 m omega x square, okay? If you write this Hamiltonian, why we are writing this way? Because if you write this, the Euler Lagrange equation, which is d over dt, dl over dx dot, dl over dx, this gives us the equation of motion, which is f equals ma equals minus kx. So this gives us the equation of motion for simple harmonic oscillator. Or in general, you have a differential equation like this, f equals ma basically, and you try to find a Lagrangian whose corresponding Euler Lagrange equation gives you the same equation of motion. Okay, this is the way we do it in Lagrangian mechanics. So here d over dt, as an example, simple harmonic oscillator, dl over dx dot is going to give you mx dot. It should be equal to dl over dx. So here we have m omega x squared x, the minus sign. So this means that you have m time derivative minus kx, which is the equation of motion we have here. So you have a differential equation, for example, Newton's F equals ma equation, and you want to find a Lagrangian, you have to guess it, okay, such that this equation, which has a standard form, Euler Lagrange equation, becomes your equation of motion, F equals ma, okay? And after you find the Lagrangian, it's easy to find the Hamiltonian by Lagrange transform, okay? This is what we do in classical mechanics. I just wanted to remind you very quickly. Now here, we are looking for a Lagrangian, which is a function of coordinates, general coordinates, in this case the field, because instead of positions, generalized coordinates in Hamiltonian or Lagrangian mechanics, we work with the field configuration. Its derivative, phi dot. What happened here? Okay, L phi dot. And also, because we are trying to combine special relativity and quantum mechanics, in special relativity, when you have a time derivative, you should have a spatial derivative as well. So, in general, Lagrangian would be a function of these. Right. So, we want to guess a Lagrangian, a function of these variables, such that Euler-Lagrange equation, which in this case would be dl phi dot plus divergence of dl d del phi dl d phi. Remember, in classical mechanics we had just this term, but here, because of special relativity, space and time treated on the same footing, we have spatial derivative as well. So you want to find this Lagrangian in such a way that this equation, the Euler-Lagrange equations, becomes your Klein-Gordon equation. And it's easy to play with this Euler-Lagrange equation and find the right Lagrangian. It's a guesswork. If you try finding the Lagrangian, you're going to find that this way it's easy to find actually. But this is just guessing. I mean, no one can give you a standard prescription to find the Lagrangian for a given differential equation. But most of the cases, it's simple. So this is our Lagrangian. If you now write d over dt, the Euler-Lagrange equation, it's going to be dl over d phi dot. dl over d phi dot comes from this term. It's going to give you phi dot, derivative with respect to phi dot, and then plus divergence of dl over d del phi, derivative of this, going to give you a minus sign here, del phi, equals dl over d phi comes from this term. So this means that this becomes Laplacian, and this is the Klein-Gordon equation we already have. So we found the Lagrangian for this equation, okay, by guessing it basically. Look at the Euler-Lagrange equation. It has a standard form. It's given. So try to play with different Lagrangians in terms of these variables to find the right function. And as I said, it's easy to do, especially in this case. So if this is the Lagrangian, what's the Hamiltonian? Hamiltonian is the Legendre transform of this Lagrangian. So instead of being a function of phi and phi dot, it's going to be a function of phi and pi, basically, some momentum, okay? And momentum here, by the way, as we defined here, I erased it. Momentum, generalized or conjugate momenta, are defined as, in classical Lagrangian mechanics, P dl over dq dot, if L is a function of q and q dot, generalized positions or generalized coordinates. For this general Lagrangian, this is the momentum, definition of momentum. So here, momentum would be dl over d phi dot, because our generalized coordinates are just fields. It's the field. So from this Lagrangian, you see that it is phi dot for the Klein-Gordon equation is simple. Okay, so the Hamiltonian would be the Hamiltonian then for the Klein-Gordon equation. Remember, this is the Lagrangian of the Klein-Gordon equation. The Hamiltonian of the Klein-Gordon equation would be, again, similarity with classical mechanics, PQ minus L, PQ dot. This is the Legendre transform of the Lagrangian to move from velocity x dot or q dot to momentum representation. Let me write this a little bit. Okay, H would be pi instead of p. For the field, we have pi, which is phi dot basically. Got it from here. Q dot means phi dot. Q is phi. Minus L. So from here, pi square, because phi dot is just pi, minus, what is L? We had L here. Phi dot square plus del phi square plus m square phi dot square over 2. Phi dot is the same as pi. So basically you get pi square over 2 plus del phi plus. Okay, so this is the Hamiltonian of the Klein-Gordon equation, right? If you write down the Hamilton's equation of motion, you're going to get the same Euler-Lagrange equation, or the Klein-Gordon equation, basically. So you have Hamiltonian and Lagrangian formalisms for the Klein-Gordon field. The field acts like a generalized coordinates, its derivatives, for example, with respect to time, acts as a momentum, so on and so forth. So here, now we have solutions or answers to these questions. What's H? We found H. H is over to here. This is the Hamiltonian of the, I try to change my color. This is the Hamiltonian for the Klein-Gordon field. We have also Lagrangian. So we found this, and pi is basically just phi dot. Okay, we found the momentum as well. So you see the similarity between simple harmonic oscillator and Klein-Gordon field. And the same thing would apply to Dirac's field, to this vector potential in the electromagnetism when we talk about quantum electrodynamics, QED. It's the same procedure. This is called the second quantization. Second quantization means that you have a field equation, one more time. For example, for the Klein-Gordon case, you have a differential equation, which is a classical field equation, right? Classical field. You take it, you find the Lagrangian and momenta, etc., Hamiltonian. It's easy, it's just classical mechanics. Then you promote the field to an operator. So the momentum as well would be promoted to an operator. Then you say that, so let me write it one more time because this is very important. Second quantization for the Klein-Gordon equation. The Klein-Gordon equation can be written like this. And again, I'm repeating myself, but the same approach can be applied to Dirac's equation, vector potential, etc. You have a differential equation. You say basically what kind of Lagrangian I should find in terms of phi dot, and del phi, because these are the derivatives which appear in this equation, to satisfy dl d phi dot plus divergence of dl d del phi equals dl d phi. This is your Euler-Lagrange equation in Lagrangian mechanics. The question is, find the Lagrangian, the right Lagrangian, whose corresponding Euler-Lagrange equation becomes the Klein-Gordon equation. If you do that, you get Lagrangian as phi dot minus del phi square minus m square phi square to you get pi, the momentum, corresponding momentum, which is phi dot. Now, and Hamiltonian as well. Okay, then you do the second quantization like this. Phi and pi are promoted to operators, exactly like in the first quantization. X and p there would be promoted to operators with some commutation relation, if you remember. We talked about this just minutes ago. So here you're going to apply phi xt, pi yt equals ih x minus y. Okay. So to finish this lecture, let me very briefly tell you the program of quantizing the Klein-Gordon field. This is the basic program we follow in canonical formalism of the quantum field theory, which is basically as follows. You have a classical field equation. For example, the Klein-Gordon equation is just an example. This is the Klein-Gordon equation, right? Or you can use drag equation to start with. For the spin half particles, you have a partial differential equation for a field, a classical field, which is something like this, I guess. I might be wrong in signs and some details. Alpha and beta are turn out to be 4x4 matrices here, but you can write it in this formalism, in this form, basically. We're going to talk about the direct equation, so I'm not emphasizing it here. But the point is that to show you the general procedure of quantizing fields, moving from quantum mechanics or classical field theory in some sense to quantum field theory, okay? And another example is the equation for the vector potential. We discussed these, all of these actually. So here we have classical fields. This is a classical field, which is a vector field. It's vector because it's going to describe photons, particles, after quantizing the field, which have spin or polarization. But this field here, Dirac's field, is not a scalar field, in fact, because you see the hint here, actually, because alpha and beta are 4x4 matrices, because you have to treat them as matrices. You're familiar with this, I guess, from elementary quantum mechanics or relativistic quantum mechanics, because if you want to have a linear Hamiltonian with respect to momentum, you have to use matrices. And it turns out to be the solution of this equation is kind of a four-component object, so it's not a scalar field. It's related to spinors, etc. We're going to talk about that. And the solution describes spin half particles. And the Klein-Gordon equation, which is the simplest field equation we have, it's just a field equation for a massive particle, mass m, which has no spin, spinless particles. And for the Dirac's field, we have this mass here. It's going to be the mass of the particle associated to the corresponding particle. Now, the canonical formalism, the second quantization to get the canonical formalism, is as follows. You, first of all, find a Lagrangian. I'm going to write this procedure only for the Klein-Gordon equation, repeating myself. What we actually discussed in this lecture, but the same approach with some, mathematical, details, some sophistication can be applied to the Dirac field as well, and also the radiation field. We're going to call this radiation field. It's the electromagnetic field, basically, and this is the Dirac's field or Dirac field, electrons, positrons, etc. You find a Lagrangian. In this case, it's a function of phi, the field, its time derivative, and its space derivative. These derivatives come from basically special relativity. With respect to time, with respect to space. You have to treat them symmetrically. And then you find this Lagrangian by guesswork, exactly like in classical mechanics. Remember, in classical mechanics, in Newtonian mechanics, you have F equals ma. This is a differential equation. For example, if this is the gravitational force, this is a differential equation for in this form. Okay. Now, this is the equation of motion. In Lagrangian formalism, you find a Lagrangian, which is a function of x dot, and probably time, but in this form, in such a way that the Euler-Lagrange equation, which is in this simple case written, can be written in this form, becomes your equation of motion. In other words, F equals ma can be written in terms of Euler-Lagrange equations, and you're looking for a Lagrangian to get that equation right. Okay, exactly the same procedure here. By guesswork, you find a Lagrangian such that the Euler-Lagrange equation, and in this case, because you have space and time, special relativity, remember, you have d over dt, dl over d phi dot, time derivative of dl over phi dot, time derivative of phi. Time derivatives go together, space derivatives, spatial derivatives go together, so divergence in 3 dimensions, dl over d, now you have space or spatial derivative, so it's going to be the spatial derivative of phi should be dl over phi. Okay, this is the Euler-Lagrange equations, and you want to find a Lagrangian, this equation, such that this equation becomes the Klein-Gordon equation. Okay, it's usually easy. For example, in this case, we got phi dot minus del phi squared minus m squared phi squared. 2. Later, we're going to add other terms to this Lagrangian, describing interactions and currents, etc. But for now, this is the main idea here for now. Okay, this is the big picture. And then from here, dl over d phi dot would be the corresponding momentum. Okay, so you get momentum, you get Lagrangian by guesswork, and from there, Hamiltonian is, just remember, in classical mechanics, p q dot minus l. Q generalized coordinates, p momentum, so here it's going to be phi dot minus l. This is Lagrangian. When you get this, you can look at this simple harmonic oscillator and do the same procedure of quantizing the field. For simple harmonic oscillator, we promoted x and p to operators. Okay. Here we don't do that. The second quantization should be done here, which means phi should be promoted to an operator, pi should be promoted to an operator. We know the same, the form of phi in terms of a Fourier transform, in terms of these operators, if you remember. I wrote this many times, a Fourier transform, you have exponential functions here and here. Now, making phi an operator means these Fourier transforms are Fourier transform of phi, creation and annihilation operators. They become operators as well. So this is called the second quantization. The only thing you need is equal time commutation relations. And I'm writing this repeatedly because this is important and I want you to remember. So this is going to be Dirac's delta function, and phi with itself, the commutation of the field, and these are fields, remember, and pi with itself all vanish. Okay, so this is the commutation relation you need, which is similar to x and p, xi, xj in 3-dimensional components, ih delta ij, delta Kronecker, and x with itself and p with itself, commutation relations vanish, so you have the same stuff here. Okay, this is the second quantization. Instead of x and p, you quantize the field and corresponding moment. Okay, we discussed this enough now. Let me show you one more thing and then we can wrap it up. In quantum mechanics, we define the wave function as the inner product of the position eigenstate and the quantum state of the system. It's a linear product. And we call this x just the position eigenstate, but no one tells you how you create a particle at point x. We say that we have a particle at point x, it corresponds to this eigenstate, and you have a position operator acting on x, gives you, this is the eigenvalue problem for, and x acting on wave function gives you x psi x. Okay. Now here we know something more. X is basically the vacuum state, no particles around. When phi acts on the vacuum state, it gives you a particle at point x. So you can write down the wave function in this form. This is an operator now, a quantum field. Okay. Now, in order to get the quantum mechanical picture, or in order to get quantum mechanics out of quantum field theory that we are developing, you should show that this function, the wave function, for example, for a single particle, let's talk about single free particle, okay? We know the Schrodinger's equation, h squared over m. Okay, this is Schrodinger's equation with no potential. So we want to show that this formalism that we are developing here is consistent. So if x, a particle at point x, is created by applying our field, Klein-Gordon field, on the vacuum state, so from this expression, at low energies, you should get the Schrodinger's equation. In other words, if you use this expression as a definition of wave function, now you have this field inside this. You should start from the left-hand side, for example, and say, well, I put this expression in terms of my field, and from here you should get the right-hand side of this equation. This is easy to do. I encourage you to do this. Next time I'll do the calculation myself in details, but it's easy, and at some point you're going to get something like this, m squared c4 plus p squared c squared, which is the energy relation, which is m squared c4 minus h squared c squared. Okay, then you would say that, well, because I'm in the low energy regime, I'm going to discard this and keep this term, okay, as a Taylor series. Then you're going to get, as an approximation, minus h squared over 2m, the Schrodinger's equation. The point is to show you that this picture that we are advertising here is consistent with our picture in terms of wave functions, etc. I guess that's it for now. Next time we're going to get back, do the same calculation, the second quantization for the radiation field, electromagnetic case, and by quantizing this field, we're going to get to the picture in which photons or particles play the main role. And then again, get back to Klein-Gordon equation. We're going to talk about, adding more terms to these equations, describing interactions and currents, sources, etc. And then I guess we're going to move to Dirac's equation, second quantization of the Dirac field, and probably then we can talk about the path integral formulation of quantum